welcome to True Projects. In this video, we are going to explain about the project that is Smell Aware Bug Classification. Before getting into the execution, first let us understand what is the project about. You know how much of what we do every day, whether it is booking a cab, managing finances, or even just watching a movie, relies on software. Because we depend on it so much, it is crucial that softwares work smoothly and accurately. But here the thing is, softwares they aren't perfect. Bugs or even errors in the code often they creep in and they can mess up with the results causing errors or even serious problems. And now bugs they don't just appear out of nowhere. They are usually the results of coding mistakes either because of rush, deadlines, lack of experience or skipping the best practices. Fixing these bugs is really important, but it is also time consuming. That is where automatic bug detection comes in. It's like training a system using machine learning to analyze the code and predict whether it is buggy or not. Here, the thing is, machine learning they can be really useful for predicting bugs in software. But a lot of approaches they miss something important called code smells. So these code smells are basically signs that code might not be structured well or follows the poor design practices. You know, things like overly complex code, repetitive patterns, or messy structure, they don't necessarily cause bugs right away, but they can make the code harder to maintain and more likely to break down in the future. If these smells aren't addressed early on, they can make debugging a lot harder. So, if we include these code smells indicators in the bug prediction models, we can actually improve the accuracy of our prediction. It's like catching up potential issues before they turn into the biggest problem. By doing this, we can make debugging process smoother, reduce the chances of bugs popping up later, and ultimately improve the overall quality of the software. So incorporating code smells helps making the whole development process a lot more efficient, leading to better performance and happier users. So what are we doing here is we are using smell code metrics to detect buggy software. These metrics focus on something called anti-patterns, which are basically the signs of bad code practices. Things that usually indicate potential bugs or problems in the software. By analyzing these patterns in the code, we can figure out whether a piece of code is likely to be buggy or not. And to make this work, we are using dataset called PROMISE, which is commonly used for this kind of experimentation. But there is a challenge in this data set. There is an imbalance between buggy and non-buggy classes, meaning here there are more non-buggy examples than the buggy ones. To fix this, we are using the technique called SMOTE, that is synthetic minority oversampling technique to generate synthetic buggy instances balancing out the data set. Once we have balanced the data, we move on to the feature selection, where we remove any unnecessary or redundant features from the dataset. This is done using method based on correlation, which helps to ensure that we only keep the most relevant features for detecting bugs. This way, we are left with the most important data that can truly help us in predicting whether the software is buggy or not. Once we have once we have processed the data and made sure that everything is balanced and ready, we move on to using machine learning algorithms to actually train and test a model. The goal here is to teach the system how we predict whether a piece of code will be buggy or not. We use several machine learning algorithms, which are random forest, support vector machine, k nearest neighbor, logistic regression, and naive Bayes. Each of these algorithms has its own way of analyzing the data and making predictions. So we want to test and see which one works the best. And to evaluate this project, we are using different metrics which are accuracy, precision, recall, and F1 score. By looking at all these metrics, we can get a clear picture of how well each model is doing and choose the best one for predicting the buggy software. This is all about the proposed system. Moving to the extension part, to further improve the performance, we are incorporating an ensemble model voting classifier. This approach combines multiple algorithms instead of relying on just one model to make the prediction. We trade several models at the same time and then let them vote one the best result. This method helps to improve the overall prediction accuracy and combined wisdom of multiple models tends to perform better than any single model alone. Moving on to the front end part, we have built front end using Flask framework. This front end allows users to interact with the system directly and they can input the data and test how well the bug prediction model works. To make sure that only authorized users can access it, we include user authentication mechanism. So, this ensures that system is secure and the users have smooth and protected experience while testing the model. Moving on to the implementation, we have followed the steps which are mentioned in the flow of work. Let us understand what are the steps have been followed. So first step involves importing necessary libraries and modules that are required for data manipulation, model building and evaluation. Then comes the exploring dataset part. This step involves loading the dataset, examining its structure. We check the data types, column names, and some sample records to understand its content. Then comes the data visualization. Visualization tools such as graphs and charts are used to explore patterns and trends in the data. This helps us in understanding the distribution of features and identifying potential relationships. Then comes the data pre-processing. Here, irrelevant or redundant features that don't contribute to the analysis are removed to clean the data set. And then missing or null values are either filled in or removed to avoid errors during modeling. And features are scaled to similar range to ensure that no feature dominates the other, especially for algorithms sensitive to feature scale. Then comes the data balancing part. The dataset is balanced using synthetic minority oversampling technique, which generates synthetic data points for the minority class to address the class imbalance. And then features that are highly correlated with each other are identified and removed to reduce the redundancy. This helps in improving the model performance and efficiency. Then, in the step that is predictors that are features and the target variable are selected. X represents the input features and Y represents the output label. Then the dataset is split into a train and test part. So train set contains 70% of the data and test set contains 30% of the data. Training set is used to train the model while testing set is used to evaluate its performance. Then comes building the model. In this step, machine learning models are initiated. After initiating them, we train it on the training data. The model learns patterns and relationships from the training set in order to make predictions on the new and unseen data. And performance of all the models are evaluated using these metrics and they are compared through the graphs. Moving on to the part of front end, a user-friendly web interface is created using Flask. It includes features like registration, login, and user authentication, which with the SQLite database, which is used for storing the data securely. And in the front end, users they will be able to give the input value, and that will be pre-processed at the back end. It will be fed with the train model. Finally, outcome will be displayed in the front end, whether the given values contains the buggy or non-buggy. Moving on to the algorithms used, these are the algorithms used for predicting the buggy classification. So we have used KNN, naive Bayes, logistic regression, support vector machine, random forest, and the extension model voting classifier. Moving on to the requirements, to implement this project, we need basic requirements, which are hardware and software. Coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Coming to software requirements, we need application of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. Now, let us execute the project. To execute, we need to open the code folder of the project. So open the code folder. These are the source code files in the code folder of the project. Let us understand each of them. How will they be used in this project? Open the dataset folder. So these are the different types of code smells. In each file, we will be having different types of data. So we will be loading all these files into the code and then we will be clubbing together and form the final data set. So this is the final data set that is used to train the models. Let's close this. And here in this model folder, we have the .h5 files, numpy files, and pickle files in which we have the algorithm information and that will be loaded into the project code during runtime of the application. And here we have static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And here we have is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And here in this test data file, we have test data that we will be using in the front end to predict the buggy or non-buggy case. Let's get back. And here This is the app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And this is the notebook file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And here we have signup.db file. This file is a database file which is used to store the user information. So now we have understood all the files of the code folder. Now let us execute. So copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Now open the command prompt. It has been opened. Now give the command cd, give the space, paste the copied path, and now click on enter. Here, if you observe, current directory is changed to the code folder's path. Now compile the app.py file. So give the command python space app.py and now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So now copy this local link provided by the Flask framework and paste it in any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. This is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So we need to sign up first. Click on sign up and enter all the registration details if you are registering newly. I have already registered, so I will directly sign in. Click on sign in. Give your username and the password. And now click on sign in. We have signed in successfully and we are redirected to prediction page of the project. Here you can see choose file button, right? We need to click on that for uploading the test case file. So click on choose file. We are supposed to upload this file. Click on open. It has been loaded. Before uploading, let's see what do we have in this test data file. So let's get back to the application. Open test data folder. Open the test data. So these are the different test cases that we have. We will be uploading them and predict whether the values are buggy or non-buggy. So the first one which we have is the name. And the next one is WMC. WMC is the weighted method count. It refers to the total number of methods in a class weighted by their complexity. A higher WMC indicates a more complex class which may be harder to maintain. And then comes DID, that is depth of inheritance tree. It is the depth of class in the inheritance hierarchy. A higher DIT indicates a more complex inheritance structure which could make the class harder to understand and maintain. Then comes NOC, that is the number of children. So this refers to the number of immediate subclasses that a class has. A higher NOC might indicate a more complex and harder to maintain class. CBO, that is coupling between objects. This measures the number of classes that are coupled to given class. High coupling can indicate that a class is overly dependent on the other class, which may make it more prone to defects. And then comes RFC, that is response for a class. The number of methods that can potentially be executed in response to a message sent to an object of the class. A higher RFC indicates a more complex class. Then comes LCOM it is, that is lack of cohesion in methods. This metric indicates how well the methods of a class are related to each other. A higher LCOM suggests that class methods are poorly related and it may lead to maintainability issues. Then we have CA, that is coupling afferent. It refers to the number of classes that depend on the given class. A higher CA can indicate that class is more critical and changes to it that could affect many other classes. C, that is coupling efferent. This refers to the number of classes that given class depends on. Higher CE indicates that class has higher dependencies on the other classes, potentially making it more difficulty to modify. Then we have NPM, that is number of public methods. It is the number of public methods in a class. More public methods may increase the complexity and interactions with the other parts of the system. Then we have LCOM 3, that is lack of cohesion in method 3, a variation of LCOM that measures the cohesion based on methods and pairs. So higher values suggest poor cohesion and may indicate a class with unclear responsibilities. Then comes log, that is lines of code. It is the total number of lines in the code of a class. A higher LOC typically suggests a larger, more complex class, which may be harder to understand and maintain. Then we have DAM, that is data abstraction measure. This measures the level of abstraction in a class by counting the number of data access methods and number of abstract methods. Higher DAM values suggest better data abstraction. Then we have MOA, that is measure of aggregation. This is a metric measures the degree to which a class aggregates its functionality. A higher MOA indicates that a class performs more aggregation, which may make it more complex. Then the next one we have is MFA, that is method fan out. It is the number of methods called by a class. A higher MFA suggests that class has more dependencies and interactions, which can increase complexity. Next we have is CAM, that is cohesion among methods. This measures the degree to which methods in a class are related to one another. High CAM values indicate better cohesion, meaning the class is more focused on a single responsibility. Then coming to IC, that is inherence coupling. It indicates the level of coupling between a class and its superclass. Higher IC values can indicate tight coupling, which may reduce flexibility and reusability. Coming to CBM, that is coupling between methods. It measures the level of interaction between methods in a class. Higher CBM suggests that methods in class are highly interdependent, potentially complicating changes. Coming to AMC, that is afferent method count, it is the number of methods that depend on methods of a given class. A higher AMC indicates that a class is more likely to affect other parts of the system when modified. Coming to max CC, it is the maximum cyclomatic complexity. It is the maximum number of linearly independent paths through a program's source code. Higher values indicate more complex, difficult to understand code, and that can be prone to errors. Last, we have is the average CC, that is the average cyclomatic complexity. It is the average cyclomatic complexity of the methods in a class. Higher values typically include more complex methods, which may be harder to maintain or debug. So this is all about the parameters that we will be giving as input. Let us upload this test case, get back to the application, click on upload. So this file will be uploaded and then we will be getting the predictions. So here, these are the test cases that we have given to the system. So the software which will be containing these values has been predicted as non-buggy. That means the software is non-buggy. Similarly, for the second case, the software which has these values will be non-buggy. Application has predicted as non-buggy. For the third case, it has predicted as buggy. Similarly, for the all other cases that we have uploaded, we got the prediction if that values, if the software contains of these kind of values, it will predict whether it is buggy or non-buggy accordingly. Here we got the prediction by the train model. So when we have uploaded the test data, it has been pre-processed at the back end and then train model is feeded with that data. And that train model will be giving us a prediction. So here train model has given the prediction. Now let's check with the graphs. Click on graph. So here, this is the confusion matrix graph of the extension. Here, this is the confusion matrix and this is the ROC AUC curve graph of voting classifier. This is the accuracy comparison graph. Here on x-axis we have accuracy score and on y-axis we have algorithm names. Similarly, here we have precision score comparison graph. This is the recall score. This is the FN score. And these are the metrics used to evaluate all the classification models. Now click on sign out. In this way, just by giving inputs to the system, based on that, it will classify the bugs. If there is bug, it will classify as bug. If there is no bug, it will predict as no bug. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.